Don't spoil it. It's called a satellite. Or if it's being shot fast enough, it's in orbit. So, going for one of those words. That's all satellite motion is. You take an object and you shoot it fast enough so that as it falls, it constantly is missing the Earth. And I think that was something from, I keep wanting to say Phantom Tollbooth. It was one of those middle school age books where someone flew by throwing themselves at the Earth and missing. That's in essence what satellite motion is. I think in essence we've covered chapter 10. So there's projectile launching, which we've done. Satellites, we've done. Elliptical orbits, we've done the Kepler bit. Escape speed, we'd already done. So this means it's time to add to our calendar over there. We have 2 things to plan. Take it back into the other room. I'll just use this. So 16, 17, 18, 19, 21, 23. So this is today. 26. Let's say the quiz on 8 through 10. A week from today. And I think I missed that November 3rd there. The MCT on November 3rd. So that multiple choice test that you took the first day, this time it's for a grade. So that's the MCT, multiple choice test. Anyone want to counter with different dates?
November 3rd, Tuesday.
Oh.
Monday.
Oh, that's right, 31 days in October. All right, so November 2nd. Thank you.
When did our second test?
Sorry?
When did our test 2?
November 2nd, you can do that multiple
Oh,
choice
it's
test.
that, okay.
Yeah, that's the second test.
What chapters is that one?
It mainly, if you have a good understanding of chapters 2, 3, 4, and 5, basically what was done for the first test, that covers almost the entire thing. There is some centripetal motion which shows up in chapter 8. There's some things which potentially you could look at from an energy point of view, which might help, though not necessary. But it's primarily just the beginning stuff. I do it at this point because there's some circular motion in there. Also, because I guess test corrections are due, Friday. And so you have another chance of having looked at the stuff somewhat recently by the time you do this. Again, on the test corrections, because I have written here the 23rd test corrections, if I'm planning to do them but don't have them ready Friday, just let me know when I'm going to see them. All right, any questions right now? All right, so 11 through 14, sort of a group. I'm going to go through 11 through 14 relatively quickly. As in, I would not be surprised if we're done by the time we have the multiple choice test. The homework for that, the quiz, what I do for 11, 14, I will at some point post your individual assignments for it. Probably if you went in right now under assignments and for chapters 11 through 14, you could click on it and you could see what people in the past have been assigned. But I just haven't done it for this group yet. So that should get posted sometime in the next couple of days. And that is, nope, that's that. We still have 6 minutes. All right, so let's talk about chapter 11. States of matter. What are the 3 classic states of matter? Raphael, you look like you wanted to say something. The 3 basic ones.
Solid, liquid, gas.
Those are the big 3 right there. Chapter 12, chapter 13, chapter 14. What's another state of matter? Usually the 4th one that's mentioned if they mention 4.
Plasma?
Yep. They don't have a special chapter for plasma. What's another state of matter? Or how many are there? Good feeling. How many states of matter are there officially at this point? There's 4 listed here. How many more? Thousands? Tens? Ones? No gut feeling at all?
I thought it was only those 4.
Yeah, it's not. I think we could be, sorry? Thousands? There might be, we haven't discovered that many yet though. Wikipedia, I think, lists about 14 of them, or so. Another one, the initial is the Bose Einstein condensate. And I bring this up not, I guess, part trivia and part, it's just really cool that it exists. So I'm gonna talk a little bit about Bose Einstein condensates. Originally theorized by Bose and Einstein. They didn't actually ever see it. They finally were able to do it when I was in grad school, able to create the first one. But if you get down into the nature of particles, all particles have what's called a spin. Now some particles are called half integer spins. So they'll have a spin of a plus or minus a half, or plus or minus 3 halves, or plus or minus 5 halves, and so on. These are called half-spin particles. An example of that are electrons, protons, neutrons. They're all half-spin particles. And then there's integral spin particles. Integral spin particles. Light is an integral spin particle. Now, the reason I bring up this stuff is that half-spin particles cannot overlap. The reason you're not falling through your chair is because your body is filled with these half-spin particles, and the chair is filled with half-spin particles, and half-spin particles will bounce off each other. Integral spin particles will pass through each other. So if I took a light beam and I shone a light to the back wall, and someone else took a light beam and showed it to the side wall, those light beams, if they hit, would just cross right through each other. They don't bounce. And you can test this. You just need two lasers of different colors, and you can see if I shine a red one this way and a green one is shown that way, that a green dot would still appear on that wall, a red dot would appear on that wall. So it is possible, though, to take two half-spin particles, and if you orient them just right, you create a whole spin particle. So in theory, what they came up with is that I could take a half-spin particle and another half-spin particle and create, well, these are really vectors. I could create a zero-spin particle or a spin 1 particle, or I guess a spin negative 1 particle. So if I could take half-spin particles and create integer spin particles, then could I possibly take let's say a helium nucleus or a helium atom, apply the right amount of magnetic fields and so forth to get everything lined up just right to create a whole spin particle. Then I take another helium atom, do the same thing to that, and now once the whole atom is an integral spin particle, I can pass them through each other. That's a Bose-Einstein condensate. You take two particles that ordinarily bounce off each other, and you get them to be in the exact same place. So a little over 20 years ago, they were finally able to do that for the first time. Which to me is just really cool. So that means, in theory, since I'm composed of a whole bunch of half-spin particles, could I potentially be exposed to some sort of magnetic field, calibrated just right, so that I suddenly become an integral spin? Which means that light would pass through me. I would be invisible. Take it one step further. I'm oriented so that now just everything's lined up perfectly. I'm an integral spin particle, or composed of a bunch of integral spin particles, and then I do the same thing to the wall. Now I can walk through the wall. So that would be sort of the science fiction aspect of it. You take this basic principle here and then extend it. In reality, we can do a handful of particles, handful of atoms. We can't do anything this big. Plasma, we'll end on the plasma note. Disassociated atoms. In other words, there's so much energy involved that the electrons cannot stay attached to the nucleus. The electrons are floating around freely, and the nucleus, which is positively charged, floats around freely. And that's all plasma is. Generally, plasma is done in hot places, such as in the core of the Earth, but the light fixtures here have plasma in them also. It doesn't necessarily have to be hot. You just need energy in the right place. And with that, I will see you Friday.